Next, we have Dr. Hitoshi Sato, who's going to talk with us about Lustre Use Cases in the TSUBAME 2.0 computer. Sorry, supercomputer. Not a new word.
Thank you very much. Hello, everyone. My name is Hitoshi Sato. I'm a researcher at Tokyo Institute of Technology in Japan. First of all, I really appreciate the opportunity for the talk. Today, I'd like to talk about Lustre use cases in the TSUBAME 2.0 supercomputer, which is a supercomputer in our university installed in last November as a successor of our previous supercomputer called TSUBAME. And here is the outline of my talk. First, I'd like to introduce the overview of the TSUBAME 2.0 supercomputer, and then I'll talk about the overview of the TSUBAME, overview of the storage architecture of the TSUBAME 2.0, and finally, I'll touch on Lustre file system use cases in our system. Okay, TSUBAME 2.0 is a green cloud-based supercomputer at our university, located near the center of Tokyo. Thanks to the supercomputer is built thanks to the NEC, HP, and other very, very good vendors, including DDN and Blue Arc related storage systems. The TSUBAME 2.0 has several notable features, such as performance. Our system achieves 2.4 petaflops peak performance, 1.192 impact performance. The result is listed 4th position in the top 500 ranking list in last November 2010. This performance is achieved by using next generation multi-core x86 CPU plus GPUs. We have 1,432 computing nodes with Intel Western Nehalem EX-based CPUs and 4,244 NVIDIA Tesla M2050 based GPUs. The system has also 95 terabytes of memory with 0.7 petabytes aggregation memory bandwidth, and also has optical dual layer QDR-IB networks with full bisection bandwidth. And the energy consumption is quite low. Our system achieves only around 1.2 megawatt power, and PoE performance is 1.28. The result is also listed in 2nd position, actually 3rd position in green 500 ranking. Derived to, this has several reasons, and we have got the greenest production supercomputer in the world as a computer, and we also provide VM operation by using KVM. By using this mechanism, we provide Linux and Windows-based HPC environment. Here is the overview of the system. Basically, we have 3 components, 3 types of computing nodes. Is this the laser pointer? Thin node and medium node and fat node. We use mainly these thin nodes. Each of computing node has 2 Intel Western EP-based CPUs and 3 NVIDIA M2050-based GPUs. And each of computing node has 54 gigabytes of memory and 120 gigabytes of SSD volumes. The difference between these computing nodes derives from the memory capacity and SSD capacity. These computing nodes are used for application that requires massive memory bandwidth. And we also had HD hard disk-based storage systems. The capacity achieves 7.1 petabyte. I'll describe this configuration later. And these components are connected by full bisection optical QDR InfiniBand networks. We also have tape library systems based on StorageTek SL 8500. Okay, let's move on storage issues in our system. In our system, basically, we have two types of application workloads related to I/O. First one is simulation and traditional HPC I/O. Application generates output for intermediate and final result. For example, application runs by using 28 nodes. Each of computing nodes has 52 gigabytes of memories, and generate the intermediate data 200 times. The situation requires 1.3 petabyte of storage capacity, and several users, typical users, execute this kind of execution several times. If 4 times, the required storage volumes related into 5.2 petabyte. And we also have data-intensive computing workloads. Recently, these kind of workloads are increasing in our system, especially this type of application is conducted for used for data analysis purpose, such as bioinformatics, text and video analysis purposes. For example, we have a web text mining, text processing application for acquiring knowledge from 1 billion pages of HTML. This type of application requires 2 terabytes of storage capacity initially, but after pre-processing, the application generates 20 terabytes of intermediate output. And finally, after the main computation, the application generates 60 terabytes of final results. And also, this type of application use commodity tools such as MapReduce, especially Hadoop, and workflow systems, and RDBs, and Fuse, and so on. However, there are several storage problems in our systems, as listed here. Support for various I/O workloads, storage usage, and usability. So let's look at these problems one by one. First one is I/O workloads. Basically, our supercomputer is designed for general purpose because our supercomputer is used for HPC service in our university. So various HPC applications run on our system. Typically, this kind of I/O generates. First one is application with concurrent parallel read-write I/O derived from traditional HPC workloads, such as MPI I/O or MPI with CUDA or OpenMP I/O. Second one is fine-grained read-write I/O. For example, a checkpoint and temporal files. By a typical case, Gaussian application. Our system, many Gaussian application is running by chemical users. Third one is application with read mostly I/O. By data-intensive application, parallel workflows, and parameter survey job by using job scheduled job schedulers, array job features, or Hadoop, or and so on. And moreover, the file system is basically shared as a single system image. So when this kind of conducted at the same time, we observed I/O concentration situation. And the second one is storage usage. Data lifecycle management is a key for providing storage services. We observed few users occupy most of storage volumes on previous TSUBAME supercomputer. This is the graph of the situation. X-axis corresponds to the user ID. On the other hand, Y-axis corresponds to its used storage volumes. Only 0.02% of users use more than 1 terabyte of storage volumes. And there are several storage characteristics, such as hard disk drives, SSD, or tape. And there are different characteristics in terms of performance, including throughput and latency, and byte per cost and energy consumption. Third point is usability. Many users want to use the supercomputer with seamless data access as their own laptop PC. So federated storage between private laptop PCs or clusters in lab and supercomputers are important. And also our system is campus IT infrastructure, so providing storage service for campus like cloud-based cloud storage service is important. And moreover, most important thing is how to deal with a large data set, especially transferring big data between supercomputer, also lab computer and their own lab computer and supercomputer is very important. This is an example we caught last year. Application user want to send their application data, 2 terabytes of initial data from Osaka to our system, which is 300 miles far between these cities. And then after the computation, they want to send back their 60 terabytes of results to their own laboratory. In this case, transferring data via the internet may take 8 days. Other solution may be FedEx, like delivery service, but these transferring big data is very elaborate effort for application users. So based on this experience, TSUBAME 2.0 is designed. This is the overview of the storage architecture. Basically, we have 5 components of storage, 1.2 petabyte of home volumes, and 3.6 petabyte of raster region, and 2.4 petabyte of GPFS with HSM memory. We also have 40 petabyte of tape libraries. And each computing node has local SSD volumes, and the total capacity reaches into 190 terabytes. And we also have grid storage for transferring big data to other supercomputer in Japan. The capacity reaches into 130 terabytes. So this storage is used for their own purpose. Home storage is used for the actual home storage for computing nodes, and providing cloud-based campus storage services. And Lustre is Lustre provides a very massive amount of GPU accelerator, but currently such accelerator doesn't support in Hadoop. So we created a simple script-based invocation tool called TSUBAME. The tool acquires a computing nodes allocated by job scheduler, then deploy a Hadoop environment on the fly, including Hadoop file system, and execute their own MapReduce application. And after the calculation, the tool destroys the environment. We also support various file systems in this system. HDFS is supported by aggregating local SSD on demand. And we also support Lustre and GPFS, but optimization is not yet. So we have experimental GPU Hadoop application system. Well, we are trying to create a tool for executing CUDA program in the Hadoop system, but this is the experiment. Okay, that is. Thank you very much for the kind attention. Any comments and questions are welcome.
You mentioned use of Ganglia for the monitoring.
Yes.
Do you also have any form of monitoring that will send out alerts or notifications based on the metrics that you're gathering on the Lustre performance?
Could you say again, please?
Sure. So you use Ganglia to monitor the performance of your Lustre file system.
Yes.
Do you have? Is there any method of sending your admins alerts if the metrics that you monitor kind of fall, beyond a particular, say, threshold or value? Can you actually inform people, give them a heads up based on the monitored information?
Actually, I don't touch the monitoring system, so I'm not sure the situation.
Okay. The reason I say this is we use a combination of Ganglia and Nagios. Mm-hmm. Ganglia provides the really nice graphs and the summary information, mm-hmm. but Nagios has very good notifications.
Mm-hmm. Thank you.
You said you created on the MapReduce stuff, you said you created the HDFS file system on the fly.
Yes.
On the local nodes. So that means that you're copying then the data from one of the other systems, from Lustre or GPFS, into the HDFS system, the input data, and then copying the result data out.
We are planning to create staging and stage out tools between Lustre file system or GPFS file system and created HDFS file system. Our tool requires to transfer their user data to HDFS region.
Yeah, my only thought there was that you're copying all the data now twice. So in other words, you have to get the data to the nodes already. So you might think about just using Lustre directly as a backing system for MapReduce. And then since you're already copying the data to the nodes, to store them on SSD, you may as well just read them directly off of Lustre.
Yeah, we currently conduct performance comparison between these two.
Next. I'm sorry.
What is your experience of reliability of running user applications on OSS? It was reported long time ago that there could be some hang up due to memory pressure, and reportedly something was fixed. So what is your experience now?
We are currently very working well. No, very not special. We don't have not special experience for now.
So you don't have hang-ups when you run Hadoop on OSS?
Sorry?
There are no issues running application, Hadoop application on Lustre server?
The application. I'm sorry. Could you say clearly? I'm not good at English.
Do you have hang-up or issues when you run Hadoop on OSS?
It's quite complicated question.
Okay, I will talk offline. Thank you.
Yeah.